Have you ever stopped to think about how we went from just a gut feeling about chance to the hardcore math that runs everything from weather forecasts to the stock market? Well, that's exactly the journey we're going on today. We're going to dive into some foundational ideas, inspired by the work of Paul Halmos, to see how mathematicians literally built a logical system to tame uncertainty itself.
Halmos kicks things off with this really powerful statement, and it's our launching pad. He's drawing a line in the sand right from the get-go. See, probability isn't just about, betting odds or philosophical musings. To a mathematician, it is a formal, self-contained system with its own rules, just like algebra or calculus.
So here's our roadmap for this explainer. We're going to start by really cementing this idea of probability as a branch of math. Then we'll learn its special language, the language of events. After that, we'll see how you actually pin a number on chance and uncover the wild patterns that pop up in the long run. And finally, we'll get to the trickiest part. How does all this perfect theory connect to the messy, real world? Okay, to really get your head around probability as a mathematical system, Halmos gives us this brilliant analogy. Forget about coin flips for a minute. Just think back to high school geometry. Geometry takes our fuzzy, everyday ideas about space and builds a totally rigorous framework from just a few basic assumptions, right? Well, probability does the exact same thing, but for our intuition about chance.
And what's so cool is when you see them side by side like this. Look, on the left, geometry kicks off with these undefined ideas like a point or a line. And on the right, probability starts with its own fundamental, undefined concept, the event. Both of these fields use these super simple starting blocks to build a complete, consistent, logical system to describe their world. One is the world of space, the other is the world of uncertainty.
All right, so if this event is the basic atom of probability, we have to know exactly what it is. It's the key. It's the thing that lets us build the entire language we need to talk about chance in a formal, mathematical way.
The definition sounds almost too simple, doesn't it? An event is just a possible outcome. So to make this really solid, we'll use the classic example, rolling a standard six-sided die. The experiment is the roll itself, and the outcomes are the numbers 1 through 6.
And this is what really makes it click. An event isn't just one single thing happening, it's a set of outcomes. The event the number is even is the set containing 2, 4, and 6. The certain event, well, that's just the set of all possible outcomes because you're guaranteed to get one of them. And the impossible event, that's just the empty set because you can't roll a 7 on a six-sided die.
Okay, now here is where it gets really powerful. We can take these events and combine them using simple logic. For example, what's the event the number is even and the number is less than 4? Well, there's only one outcome in both sets, the number 2. Or how about even or less than 4? By applying this kind of logic, we create this airtight, formal structure for talking about any combination of outcomes you can imagine.
So, we have a language. We can describe any possible outcome of our die roll with perfect logical precision. But there's a huge piece of the puzzle missing. How do we put a number on it? How do we go from describing what could happen to measuring how likely it is to happen?
This is the next crucial layer we have to build. We need some kind of function that can take one of our events, one of those sets of outcomes, and assign a single number to it, a number that tells us its probability.
And that function has a name, a probability measure. It takes any event we give it and spits out a number that represents its likelihood. But, and this is key, it can't just be any old number. For this whole system to be logical and not fall apart, this function has to play by a very strict set of rules. We call them axioms.
And here they are, the 3 absolute non-negotiable rules of probability. First, the probability of any event has to be a number between 0 and 1. 0 for impossible, 1 for certain. Second, the probability of the certain event that something will happen is always 1. And third, if 2 events can happen at the same time, like rolling a 1 and a 6 in a single throw, the probability of one or the other happening is just the sum of their individual probabilities. That's it. Every single rule in probability theory is built right on top of these 3 ideas.
Okay, so with our rules in place, we can start asking some really deep questions. What happens not just in one little experiment, but when we do it over and over again? Thousands, millions, even an infinite number of times. This is where the math starts to connect back to our everyday intuition about how averages work.
And that brings us to one of the most famous theorems in all of math, the strong law of large numbers. It sounds a little intimidating, but at its heart, this is the theorem that promises our mathematical theory isn't just some abstract game. It guarantees that the probability we calculate on paper and the results we observe over many, many trials will eventually line up.
So, in plain English, this law just says that if you do something enough times, the fraction of times you get a certain result will get incredibly close to that result's theoretical probability. It's the reason a casino knows for sure that it will make money over millions of hands of poker, even if it loses big on any single hand.
You can actually see the law in action right here. Look at the bar for just 10 coin flips. The result is all over the place. Maybe 70% heads, it's wild. But as you crank up the trials to 100, then to 10,000, you can see the observed result just relentlessly homing in on that 50% line, the true theoretical probability. The law of large numbers guarantees this is going to happen.
Now for something that's, just completely mind-bending. What happens when you don't just count how often something happens, but you start adding up the results of a whole bunch of different random things? You'd probably expect the result to be even more random, right? Well, it turns out you find the exact opposite, a stunning universal pattern.
And that pattern is described by something called the central limit theorem. What it says is that if you take a ton of independent random things, and it doesn't matter what they are, they could be die rolls or stock price changes or whatever, and you add them all up, the distribution of that sum will always start to look like one specific shape, the famous bell curve.
The implication of this is just incredible. It's the reason the bell curve shows up literally everywhere. Think about the heights of people in a population, or small measurement errors in a science experiment. These things are often the result of many, tiny random factors all being added together. The central limit theorem tells us that the result of all that randomness isn't chaos. It's a predictable, ordered pattern.
So, we've built this beautiful, abstract machine of probability theory. But this brings us to the hardest question of all. How do we connect this perfect mathematical world to a real-world problem, like what is the actual probability of a specific coin landing on heads?
And here's the catch. It's a really big one. The mathematical theory of probability, by itself, cannot tell you the probability of any real-world event. It's a system for calculation. All it can say is, hey, give me some starting probabilities, and I'll tell you everything that logically follows from them. The math is this incredibly powerful engine, but it needs fuel, and that fuel has to come from the outside world.
So where do we get that fuel? Well, in the real world, it comes from two main places. We can use what's called a symmetry argument. We can look at a fair die and say, well, it has 6 identical faces, so let's just assume each one has a 1 in 6 probability. Or we can do an experiment. For something like a thumbtack, which has no obvious symmetry, our only real option is to toss it 1,000 times and just use the frequency we see as our best guess for the true probability.
And this really is the fundamental takeaway. This entire, logically perfect, absolutely rigorous structure of probability theory is built on a foundation of initial numbers, those first probability values that have to come from our assumptions about the physical world or from our observations. They don't come from the math itself.
Which leaves us with one last fascinating question. The math works perfectly once we give it a starting point. But what's the right way to find that starting point? Should we trust pure logic and arguments about symmetry? Or should we trust empirical data and just observe the world as it is? That's the boundary where mathematics meets philosophy. And honestly, it's a question people are still wrestling with today.